Hey, welcome and welcome to AI Sweden. Before we start the event, I have to announce that we are recording it and we are taking pictures. If you don't want to be in them, please reach out. I am Vinuta. I'm a computer scientist. I work as a senior data scientist here at AI Sweden, working mostly with space-related projects. This is our primary mission. I would like to introduce what we do here at AI Sweden. I know there are many international participants today. We are very happy to have the international participants and of course the local ecosystem here. So why do we do this? What is AI Sweden for? Our mandate is to accelerate the use of AI for the benefit of society, of competitiveness, and everyone living in Sweden. We are a national center. We are neutral and non-profit and broadly funded with all three of private sector, public sector, and academia. So we have around 120 partners it's a broad range with a maturity range from not doing much AI and really being on the edge. So within AI Sweden, we have the competencies to help the partners to get at various levels while also doing cutting edge work. So space sector, the projects and ideas in the space sector are growing within AI Sweden. From this perspective, we see that with our partners, we see that our technology expertise is gathered by our partners here at RISE. We have excellent collaborations with them, with Mila, with Chalmers, UNIBAP from the private sector, LIU, ESA, LTU, of course. And we also have Maxar now as a new partner who can provide data. So the blue parts show the pillars that we have, which augment these knowledge and resources from the partnership network from our own pillars here in AI Sweden. So why are we here? So we are launching. We have launched PhiLab at Sweden. So we have an agreement with the ESA, and this PhiLab is built on top of the Edge Learning Lab, which is physically located in Gothenburg, but accessible from anywhere. The broad goals of PhiLab Sweden is to be a breakthrough lab and focused on innovation and commercialization, primarily on Earth observation. But we are starting to see from our partnership network and interest from our universities and abroad, it's also about space, what's out there. So we have just started. It started from the arrival of the research fellows, Pablo and Gabriele, who we are very happy to have. And we've just started. So what do we have now? We have close partnerships. We have a lot of close partnerships and a network of competences. We have projects in space, concretely. That's the Space Data Lab and Space Edge. And we have access to data, which is primarily managed by RISE. And we do have hardware setup with devices from UNIBAP, which is in the Edge Lab. So what can we do together? So this is, to us, PhiLab is about collaboration. It's about how can we build stuff together. We think that no one company or a few individuals can accomplish what we can accomplish with the whole ecosystem. So we are really interested in collaborations. So you know what we have now. We are very interested in conversations about ideas, about what we can already do with what we have, or about project and partnerships. So the agenda for today, a few words from Tobias from Rymdstyrelsen, who have been excellent partners and collaborators to us, and of course, a keynote from Rochelle from ESA. Then we will have a short panel discussion and then presentation on research on what we have already started to do together and breakout rooms so we all talk and get to know each other. So without further ado, Tobias, please.
Thanks, Vinuta, and thank you all for being here, and thank you also you who are on the web. And I think this is so nice. I'm so happy about this, actually. it started, I think, I started at the Space Agency in 2018, and we were discussing and see, okay, what can we do with data exploitation? How can we get better benefit from space data? And we started to say, okay, AI, well, that's something that's not new, but it's coming. Everyone was saying AI at the time, so I shouldn't be too proud about it, but that was how it was. And then AI Sweden, we saw in the newspaper, okay, AI Sweden, the government will make this center. And we thought, yeah, well, Space Agency, we must be part of it. We must really use this to promote AI and space and bring it together. So that's actually when it started, 2018. And then we had the Space Data Labs, this Swedish Space Data Lab in 2 sessions. And we always had the idea that we should really promote AI and space. It was very much about AI and Earth observation, which is really good, which is the low-hanging fruit, I would say. And when we were in that process, and we have of course been talking to ESA all the time as well, then we thought, okay, if we can bring them together, AI Sweden and ESA together, and see, okay, what can we do about this? And that was when the Edge Lab were fairly new, actually. And then we had a discussion. It was like, okay, we can do that and we can do that. It was a bit difficult in the beginning, actually, to really say, okay, but how can we make a cooperation regarding this? So we started, we had the SPOC, the Space Proof of Concept, to work with, okay, it was a hackathon working with space and with Earth observation and the Edge and so on. And ESA was involved, and we had actually global participants. It was quite amazing sitting there in Gothenburg, and then it was people connected from US and from all over the globe, actually. And then it was like, yeah, but this is actually the thing. This is what we want to do. We want to have this kind of laboratory working with the capacity from this Edge Lab, Edge Learning, and connect that with space, and not only Earth observation, but space in general, actually. And then after a few meetings, I would say, discussing this and discussing with ESA and so on, then we actually had the opportunity to initiate this during the spring, and now we're here. So I think it's fantastic, and it's definitely more than I actually hoped for when this, for me at least, began in 2018. So thank you very much.
Great, thanks, Tobias. I think we can start with Rochelle's presentations. Dr. Rochelle Schneider is staff from ESA. She will talk about health applications on top of the space data. So,
okay, first of all, thank you for having me here today. I'm very happy to be with you in this kicking off this collaboration. I think it would be a great outcomes. We will have great outcomes from this idea. Thanks, Gabriele, for inviting me to join you. And today I'm going to talk about, of course, what we are looking for about AI applications in Earth observation domain, but with an addition of benefiting public health in the activities that we do. Just before we start talking about that, I'm just wanted to present to you the fill-up. Unfortunately, I don't have the pictures of all my colleagues, but here, let's say it's a representation, a Playmobil representation of us is a fill-up. So what we do, we connect the value of Earth observation and Earth observation related products, for example, the Copernicus program, with multiple activities at the fill-up, and also in this case is benefiting multiple end users at the end of our activities. So I think most of you already know about Earth observation, or maybe never heard about using satellites, so we are very AI focused in. So I'm bringing to you very quickly some explanation, some ideas of what else we can do with other satellites, what are not Earth observation, for health applications. Let me just go through the idea of this video is just to show you some navigation satellites flying around Earth. And they are there to allow us to give the information from our location. So they allow us to, with the GPS tracking device, in our cars and in our mobiles, they allow us to do multiple activities. So these technologies have grown massively in the last years, and this helps a lot in the healthcare market as well. So for example, if you are doing exercise, this type of GPS can track the accurate location, where are you going, and then link this information with other features from inside your wearable computing device. And in this case could be, for example, linking the location by the number of steps, and linking your heartbeats with the exactly location where there is a peak of your heartbeat and what potentially happens in that specific location. And then can also this linked with IoT, Internet of Things, that can link exactly, for example, your air quality network system in that specific city, and trying to understand where you're doing the exercise, your heartbeat, and at the same time, what's the pollution level in that specific location where you are. But this is not only about gadgets, but also important to people that needs assistance. So in the case that people that have illness or disability and needs help to, for example, Alzheimer's, and needs help to track and go back home safely, these satellites are also able to provide this information. And also the medical delivery drones, when we have when we need to provide medicine in conflict zones, also these drones with GPS allow us to deliver the exact location where the people needs these medicines. So we also have the telecommunication satellites. In this case, they are really far away from us. They are at 36,000 kilometers above our heads, but they are still super relevant for us for watch, for example, television programs that are provided by directly reception or by the cable distribution. And even if you are, for example, in a city that a massive event is happening, but you're staying at home, you are anyway able to watch this from home. And then this potentially is transmitted by our telecommunication satellites. So in many countries, the telecommunication satellite provides also internet, and this is very beneficial for teleeducation and also telemedicine. So allowing us to treat people far away from us and through this telecommunication system. And what we are doing today is also enabled by the telecommunication satellites, these video conference systems that allows us to talk with each other. And for example, if a doctor needs help someone that is injured in a ship, is also enabled by this telecommunication system. So this is just to wrap up this idea of beyond Earth observation satellites, but in this case, we have two different space science. In this case, is inside the International Space Station and also in the Mars missions. So in the ISS, what we call it, is there is a lot of medical technologies happening to develop the health and safety of the astronauts in space. But these innovations, they later on come to us. They transfer from what has been done to help the astronauts for helping us on Earth. So for example, the MRI scans, the machines are something that was developed to be used in the ISS. And the famous one during COVID lockdown is the touchless infrared thermometer that we used a lot, and we are still using a lot. It's something that was developed to be used in the ISS. The ISS is a unique lab as well for us to understand how space affects our health, and then the astronauts gives us this enormous opportunity to understand many aspects of being exposed to this space environment, because on Earth, we are protected by the Earth atmosphere and the magnetic field, but outside they are exposed to, for example, low gravity, which can move a bit the organs inside the body, and also the space radiation coming from galaxies and the sun. And for example, just for you to have an idea, 1 week of exposure in the International Space Station represents 1 year of us on the ground. So it's a very it's a high exposure of radiation, and this can cause, in terms of health, aging effects, problems, problems and also the bone loss. And now I'm going to move to the Earth observation satellites, which for those that don't know about them is satellites flying around Earth and looking down and then measuring different information about our planet that we use for multiple applications. And in this case, I'm going to show you some examples of what we had already current missions under development and under preparation in 3 different lines of activities that is coming from ESA side. Of course, I'm not going to show you all of them, just for you to see the number of information that we have in preparation and in development from the ESA side. So we also have what I mentioned, digital twin engine, which here could be, let's say, named as a satellite-based data. So when we have data collected, but then used later on in modules that are mathematical functions about the physical and chemical reactions of the atmosphere that provide us information, seamless information about Earth. And why satellite-based data is because they offer inside of these models to adjust the mathematical functions, we insert observations, what we call it, let's say that we assimilate observed data to help the model adjust with the real measurements that are taking place. And in this case, you see here some examples that there's a lot of satellites being used for that purpose. In terms of satellite data collected by satellite and used directly by different applications, I bring to you 2 examples. For example, we have a land cover, which is an interesting information. For example, when we have a presentation that an example that I'm going to show you later, when you have a forecasting system for infectious diseases outbreaks, we use land coverage to allow us to understand the different patterns and behaviors in different locations. So this is quite relevant. And also for some studies or understanding the impact of the physical and mental health impact of being next to a park, a green area, a forest, is also being, the data from satellites is being used for that. Nighttime lights also are important to understand the socioeconomic information on that specific place and also the growth of that region. When we talked about air pollution, for example, we have data directly from satellites and also data that is later on being used by different satellite-based models. And in this case, you see an example of the same variable being collected by satellite, but later on modeled in this type of modeling system, because as you see on the left, you see some this specific day in the white areas, you don't have data because of the natural system of some measurements from the satellites. When it's cloudy, you don't have information. So the models allow us, of course, with a prejudice a bit of the resolution, but allow us to have this information with no missings. And when we talked about pollution, here we collect aerosol, but for health applications, we are very interested in fine particulate matter, which is called PM2.5, and this is not directly measured by the satellites. So we have to have the help from the model data to extract this information from the total quantity of aerosols. And the same thing happens here when we talked about the nitrogen dioxide. In this case, is a gas, is measured by the satellites in, for example, Sentinel-5P. And we also have the same representation in the modeled version with a coarser spatial resolution. And we also moved to the pollution, and we also have the climate. We have temperature, humidity, which is very important for when you need to understand the exposure of us in an urban heat island in a city, or when there's a high humidity, and this has a direct impact in the population. For example, high humidity might translate with fatigue, heat exhaustion, and in the low humidity, you will also have other health-related problems. So here is where we do the environment health data synchronization. You see that there are different spatial resolutions. And when you talked about health data, you might have as well different spatial resolutions. So if you're dealing with mortality data, hospital admissions, and other morbidity information, this might come to you at individual level, at the census level, or maybe at city level. And then when you connect the satellite data or the model data with this information, you have to synchronize this information. So here you see some examples of, let's say that your census data has an exact resolution of 1 kilometer, which is these blue grids, and then you need to synchronize this with the environment. And then you have different values assigned for different census tracts in this case. So here was a video to show you just the idea of having this 3D representation of time, space, and location, time, space, and you can see in here that you can track the information in different locations and in the exact time, or in different times in different locations. So this is the benefit that you can have this spatial temporal information from satellites. Okay, so now two examples of what we have been working at the PhilLab in terms of AI for health, after showing you some of the data that we use quite a lot for that. So as I mentioned a lot, the air pollution is quite important for us because we use this exposure, what we call it is the concentration of different pollutants that humans can be exposed. We analyze the risk of being exposed to that and develop some excess deaths or some specific diseases later on. So here I bring you an example of the Great Britain. And here you see that in the most of the environmental health studies, on the left, you see the data that they use in terms of environment. So the ground monitors for that. And then on the middle, you see synthetic locations of people. So when you overlap them, you see that you have a lot of people living places where you don't have measurements of the exposure for a specific environmental hazard that could be pollution or high temperatures. So this is the benefits of satellite and machine learning to help us to reconstruct these areas with no information. So the way that we do that, as I showed you before, we grab a lot of information, useful information from satellites and satellite-based data to understand the environment and then help machine learning algorithms to understand these combinations and allowing us to use this learning to estimate in other areas later on. So here you see the chain of this process. We start with our ground truth, which in this case is the monitors, and then you see a lot of relevant information that are the predictors that we use to estimate later on. And in this case, we could use a single learner, one machine learning doing the job, or if the job is very complex because the behavior of the information that we want is very heterogeneous, we might need to ask more help from other machine learning architectures. In this case, we started using ensembles. And then the picture on the right, you see the reconstruction. So you have this at human level, because this is something very important as well. We need the concentration in the area where people live to be able to assign later on this information to the health data. And I will move quickly because I'm already out of my time, but just to show you here the full chain in AI for health and also for policy guidelines. So you see in these pictures, for example, that there is a trend of reducing PM2.5 over the years, and we use this information to assign daily variations with, for example, daily numbers of deaths in different places. And then we are able to calculate the excess deaths caused by pollution with the help, of course, with the epidemiologists on that. But the World Health Organization, European Union, and also the UK, they implemented their own regulations and guidelines. So we can also analyze these guidelines if they are aligned with the concentrations in different places, and then we can also make inference about that. So the next project is a very important project for PhilLab and for all the team working on that. As you see by the names in this slide, there is a collaboration from UNICEF, multiple offices in UNICEF, and also other organizations that join us. Because in this case, it was the user that came to us and asked to use Earth observation to help the forecasting dengue outbreaks in Latin America. And then in this case, we started exploring Brazil because the quantity of data and the interesting behavior of dengue cases in the area. Because you see on the image on the right is the exactly representation of the states on the left. So each box shows you the time series changing by month and changing by year. And of course, all of them are on rates by population. So you can actually compare these from one state to another. So we, again, we collect all the information from the Earth observation. In this case, we also bring information from socioeconomic data and meteorological information to help us to understand the heterogeneous behavior of dengue incidence rates in each specific state and allow us to predict 1 month ahead what's happening in the area. So here is the first idea of the AI framework that we have used. In this case, we have to use a lot of predictors. So we had to use a data reduction. In this case is the PLS, the partial least square is like a principal components to reduce the complexity of the number of predictors that we had. We also had some correlations between different states. So we also brought information about this through the spatial correlation. And as I mentioned before, the ensembles, because in this case was so heterogeneous, the seasonality, the different low, very low cases, very high cases in different states that we had to bring a machine learning ensemble strategy in this case. So here is more detailed framework just to show you that the UNICEF, they are very focused on children. So they come to us and say, okay, it's normal, is usually you predict, you forecast using the total population, but we also would like to have a specific forecasting system for children 0-19 years old. So in this case, we had to split up the output of the model in 2 outcomes because of the request of the user. So just to finalize, this project is not aimed just to use machine learning using Earth observation with an interesting topic. That was actually a request from them that we were able to replicate this in other countries that do not have the same amount of data of Brazil. So we were transferring the trained algorithm to one country to another. And also everything that we have done we created a guidebook where people can access the data, access the algorithm, access all our mindsets in building this AI framework for replicating this not only in Latin America, but other countries. And we are very happy to share that this was a multi-award winning project. This was recognized by UNESCO, was also listed by UNICEF of the best research of the year, and also recently, because this was a study that we did not make operational, unfortunately, but fortunately, Wellcome Trust is supporting this project to make this a website where this model can be finally operational in different countries. And I will stop here. I hope that I didn't talk too much.
Not at all. Thank you very much, Rochelle, and let's thank our speaker for a second. So I think we can use the opportunity. Let's take maybe 2 minutes for questions. Are there questions from the audience here or online? You can post them in the chat if you're online, and we'll happily take them. Okay, then I think actually, or was there? No. Then I think, or is there online a question? Okay, then I think we can merge it, because the next step that sorry, were you raising your hand? No, the next step in the question, in the agenda now was that we do a little panel discussion with Rochelle also, and I would like to invite up Tobias again, also briefly introduce, and Pablo, by the way, also for the people online, was mentioned, and there's also my colleague Gabriele, please. And because what we also want to do here is, so Rochelle gave a very good overview of the benefit that you can get out of this kind of data, and we wanted to discuss a bit with you where we can take this basically. And we welcome all questions from the audience. But I think actually I would like to start with one, because what I found very interesting just hearing this now was that you mentioned that the experts came to you. And this is something I find very interesting, because we have this wealth of data and this problem of connecting these domain experts and actually the people working with this data. So actually, does somebody from the panel, Rochelle, you of course as well, what do you think is the best way to achieve that?
Oh, you start with the easy questions, I would say.
Well, with the limited time we have to
but I think that you need to have the discussion going on, actually, that you need to talk and you need to understand. I mean, if you have independent of what domain expertise you have, you actually need to understand that, okay, this is not freestanding. And if it's, when we're working with space data, it's so easy to think that, okay, if everyone just knew how good it was, then we would be at home, and then it would be so easy. But it's actually not that. I mean, it's both about other people understanding what you are knowing and what the knowledge you have, the expertise you have, but also for you to discuss with them and see, okay, what are their actual needs, so that you make sure that if you suggest something, then you should suggest something that's actually answering to a really relevant question. I think that's what's happened here. It's the discussion that's been going on, the dialogue about what are the needs and what can we do, and also maturity in what kind of information different kind of organizations need to have. I mean, I've been in projects where it was like, okay, we make this really good map, and then it's a question, okay, but how should we use that? I mean, we don't have a GIS system. Okay. Okay, you don't have a GIS system, but that makes it much more interesting. And then we really started in the wrong end. So it's really about what kind of information, how do you need it, when do you need it, what should you use it for? And often you actually have, I mean, you can have, and I'm talking a bit too much, but you can also have the expert that you're talking to already thinking that they know what they want and saying that to you, and then you listen to it, and then you try to, okay, we try to do what you wanted, when they actually, you should have asked them, but how should you use it in a different way? So back to the dialogue.
I think maybe Rochelle, would you like?
This is exactly what's happened. Is a great example, because this is exactly what UNICEF worked with us. So we started with no projects, and the UNICEF came to us and say, we would like to use Earth observation to help in Latin America, but we don't just want to use AI and Earth observation. We would like to make this enable this in other countries with not enough information, if like a perfect model where you can use everything that you want, but then when you move this model to another country, they don't have half of the data. Of course, we are not talking about Earth observation, but we are talking about socioeconomic information. So population, number of dengue cases, so they don't have the same. So we had to be aware when we were building up our AI framework that this could happen in other countries. So we had to adjust a model that could be perfectly replicable in places where we know that they would have this amount. So it was more relying about the Earth observation data, more on satellite-based information than actually specific benefits that one country might have in relation to another one.
I think the best way is to have a dialogue and to have ideas about where we want to go. If you start with just the data, let me use this, let me do something, I think it gets you only a certain way. So I think that's true for probably all data science projects. So
we actually have a question from online now on the project. So did it also involve collaborations with local universities in Brazil, Rochelle?
Yes, we had, of course, in this case, we had a collaboration later on coming up to the project. It's also integrated in the awards that we got it. This will come out in December. UNICEF will announce that, so everyone will be named there. We are very happy with that. And we definitely had to have help of the locals, the local academics, and also the health institution in Brazil, to help us, because they have full knowledge about for example, the dengue information. So in this case, they collaborated with us to understanding how the data is collected, if it is suitable, how is the different, because we have collected 20 years of data. So they have questionnaires in the hospitals about the dengue cases that might change the questions along the years. So we had to have experts in the field to allowing us to understand better how we could collect this information.
Thanks. A small follow-up question actually related. I think there's also what is then basically, you mentioned, I think the trouble of getting it kind of into production. So there came the question, so how do we use it then to empower this community to make decisions based on it, or to get the best out of it? Or also maybe what were the challenges? Because I think you mentioned that this was one of the difficulties.
When we deal with Earth observation data, it's overwhelming for people that never worked with that before. So not necessarily when you say, policy makers will not don't know how to handle this data, but when we moved for people, epidemiologists, they are brilliant in dealing with complex information that from the remote sensing perspective, we don't know how to deal with. So the same thing happens when they have to deal with satellite information. So this multidisciplinary, let's say, group, it's perfect setting for allowing the learning, transfer the learning, and also allowing capacitated in other applications that are not the common ones in the remote sensing. And in this case, what we proposed was doing this guidebook, where we wrote exactly what we have done, where we took the data, how we took the data, what is the algorithm in R and Python that we have used to do exactly what we have done, for people to understand what we have done and then try to do this in other places without us, but with our mind and brains written in this guidebook.
Thank you. I would take a question or pose a question to the panel, actually a bit transitioning, because so we spoke kind of about now the topic of what we can do with this data, but the big question is, of course, also what we want to go to next in a second is how we actually go into the topic of onboard machine learning. So actually, maybe in relation to the presentation, but also your thoughts. What do you think is the next step now between these two, basically? So if you look at this topic, for example, Rochelle, I'm asking you again here and making use of the opportunity. If you would think of what would you do? What do you see in a onboard application, for example, or do you see one, or is this a topic that you have not thought yet in this context of?
Actually, I'm super passionate about this topic because it's really relevant in multiple ways in making us using more AI capabilities directly on space. But also, for example, when we talked about health, we talked about disasters, and then we talked about a flooding disaster happening suddenly in a place. So when we have, for example, a satellite that is able to flag this immediately in the level 0, and Gabriele can talk more about that, flag immediately a volcanic eruption, a wildfire, and then tell us in the exact second that this is happening in that place, we can move there and prepare and reduce the consequences of this disaster in that specific place.
Yeah, I think. Let's see, do we have any more audience points for the panel discussion? Because I think otherwise we're kind of naturally transitioning now to the next point. Let's see. Actually, I have one more question here that came. I think you mentioned the guidebook, Rochelle. Where is this accessible? Is there a URL for it, or?
We are building up a GitHub where we have the algorithms and the guidebook together, and we're going to release it soon for people to access this information. So we'll be in the Philab GitHub. Perfect.
Thank you very much. Then does the panel have more points? Otherwise, okay, I think then we'll close this for now. Thanks to you again, Rochelle, and you all as well. Yeah, thank you very much. Before we move on. And then we will also transition to the next point in the agenda now, which is the kind of this transition that I was mentioning before. And let's see, yeah, we have the presentation now is basically focused on this a bit more the next step in this pipeline.
Okay, I think I can start. Perfect. So thank you again for attending. My name is Gabriele Meoni, and together with my colleague Pablo Gomez, today we'll try to present our research proposal for the collaboration between AI Sweden and the European Space Agency. More specifically, we will present our research plan and more or less the objectives and what we want to achieve. But let's start a bit with who we are and where we come from. So my colleague Pablo actually comes from the Advanced Concept team. That's one of the ESA team from the Directorate of Technology, Engineering and Quality. And they are trying to identify and study technologies and ideas that are strategic, will be strategic, especially in the long term, in the long future. I was also part of the Advanced Concept team, but now I'm part of the PhilAb. It's actually another laboratory in the Directorate of Earth Observation program, focusing on accelerate the future of Earth observation by ensuring transformational innovation, not only from the research point of view, but also from the business point of view. One of the points in common that these two labs, they're also focusing, including all their projects on onboard machine learning. But let's try to understand why onboard machine learning. And to understand this, please take a look at the picture. So what's basically has been done so far, what we call classical approach. We have constellation of satellites. They basically acquire data and then they download when they are close to the ground station. So the ground segment collect the data and then they distribute to the end user. This is perfectly fine when you want to distribute a lot of data, but this is not the best approach when you want to have actionable information. So you want, as Rochelle was saying, forecast a disaster that you spot from the satellite data, you want to know that immediately or as soon as possible. And that's what you can do if you apply edge computing on board satellites, basically. So you can collect actionable information. Of course, you need to provide your satellites of computing capabilities and the idea that you can make your system more efficient. For instance, you can remove cloud cover data and download only the good ones. You can make it more agile. As I said, you spot the disaster as soon as possible, you send it. And then autonomous, if you have satellite and you have information on board, you can actually make TP&Q systems where more satellite collaborate for single applications, and then flexible, reconfigurable, scalable, because they need to deal with less data to download. But of course, you need to have computing capabilities for it. So you need to have sufficiently performant hardware. That has been not always the case, because of course, so far, most of the satellites has to perform very limited number of tasks on board, mostly compression and basically housekeeping and other few applications. But now, with the advent of machine learning, when the interest to apply this on board, of course, the request for different hardware has been, of course, of a major importance. And we are actually going to this direction. So we are not only considering space qualified hardware that usually is not optimized for performance, is more optimized for safety and to be reliable in space hardware, but we're also considering for different missions, commercial off-the-shelf hardware that was, of course, tested to be resistant under radiation. So for example, if you consider, for instance, the FISAT-1 mission, we use a VPU, a visual processing unit to process and to check if there are clouds in the images. Then with OPSAT, you have also FPGA and other devices on board, and then the Unibab Space Cloud IX5 for the wild ride missions and others. So one of the things that these missions has in common, that they focus mostly on the inference and some of them only one single satellite. But we would like to do a step basically far, and we would like to focus with this research goal on the first hardware demonstration of the centralized edge learning. So actually learning on board the satellite for Earth observation application. That's basically our primary goal for the research. And if you take a look at AI Sweden and ESA, you will see that they are a lot complementary for this, because AI Sweden has basically a lot of expertise on edge learning, and not only expertise. They have the edge learning lab that is equipped with a lot of hardware that also contains some of the devices that I showed before. And also they are fully immersed in the Swedish space ecosystems and allows to talk basically to you people for eventual collaboration and so on. And when talking about ESA, of course, they have more expertise on space missions and application for more machine learning and how to perform more machine learning. And that's not just an idea. Indeed, like in March 2000, so basically this year, 2022, ESA and AI Sweden signed a letter of intent, and then afterwards an agreement to work together on edge learning for onboard application, in particular Earth observation applications. And they did it by based on this research plan that we envisioned that because it tried to take into account most of the problems that you might have when you want to train on board. Starting from the fact that you probably, if you want to do continual learning and acquiring data and learning on that, you will not have labels. So we want to use semi-supervised learning for it. Then, of course, you need to train in systems that are not so friendly. You might have a lot of problems that Pablo will talk about in details afterwards. So we want to simulate that. And when we have that, we would like to move on real hardware to make demonstrators and then try to apply to different applications to demonstrate the potential of it. Now I will hand over to Pablo that will talk more in details about it. Please.
Yes, so first off, yeah, I mean, one thing, of course, we're not in Gothenburg, and I think this brought up a bit of confusion, so I'm briefly gonna point it out. So Gabriele and I are now in Stockholm. The Edge Learning Lab is in Gothenburg, and we will visit it already, and we'll be doing that more. And we're, of course, interested in collaborations here, there, and all over Europe, basically. So this is just to get that confusion a bit out of the way. And yeah, now a bit more concrete on the actual implementation steps, because the first step, so the reason we came in this proposal up with the semi-supervised learning, meaning that you have some labels but also unlabeled data that you use, is because we too had a work last year called MS Match, which you can see here, which was based on creating such an approach where we were able to perform a classification task on 2 different data sets, Eurosat and UCM. Former is actually Sentinel-2 data, with just 5 labeled examples for each class. So of course, not eliminating the need to have labels, but reducing it to a point where you can say that I need to have only very little training data before I can enter a state that I'm not dependent on these labels. Furthermore, the approach actually, we showed that it translates quite well to multispectral data, which is in terms of Earth observation particularly interesting. But now so this is what we already have, but what we need next is that we want to look into this decentralized learning part, where we now want to take this particular method that we know works, that we've shown to work, and create a decentralized version of it, where we run it on multiple devices, so imagine satellites in this case, of course, that acquire different data simultaneously and train a joint model. Because if you think back to if you have a satellite constellation, this is the operational scenario that you would be facing. And this is actually currently being implemented as part of our collaboration by our colleagues partly in Gothenburg. And it's the first step that we had. But there's one problem here, because you can find a lot of research in this area that goes in a bit in this direction, but quite quickly you realize that there's the problem that reality is really not that simple, because training on board the spacecraft has a very different environment than, for example, on a car or on a mobile phone even. And this is kind of the second step, which we are also incorporating already to account for these operational constraints. And to give you a bit of an idea, the things that you're faced with, if you want to look at machine learning on board, but not only, then you have a limited power budget. You have solar power windows where you are charging. So you have power constraints on performing training or inference, or actually whatever activity you are performing. Secondly, you have radiation up there, which can lead to kind of unexpected behavior, like random restarts of your device, or you have corruption in your memory, which is not something you experience on Earth a lot, unless you're a very large supercomputer, for example. But yeah, that is another one. Then you have bandwidth limitations, be it in the communication to the ground or also to other satellites. Then you have a limit on what you can transmit, and also depending on the communication channels. Thirdly, the fourth part here is that you have the windows. If you imagine you have the ground station, you're not always in contact with it, and also the other satellites. And there are also aspects like if you use optical links, which are quite promising now, then you can also have problems, for example, with atmospheric conditions, clouds, and so on. So this is another constraint. And then on the right here, so of course, if you have a large GPU at home and you train something for 12 hours, you know that they tend to get warm at some point. And on a satellite or a spacecraft, this problem is quite a lot worse given the problems with the radiating heat. So this limits you in terms of how much you can do this on board. And you need to consider it also in terms of if you're currently in the sun or in the eclipse, meaning in the shadow of the Earth, because that, of course, also affects your spacecraft. And finally, then, of course, a mission, be it an ESA mission or any, oftentimes has very many different goals and people using different instruments and performing different things. And you usually not, it's not your private PC that you decide, now I'm going to use it for 12 hours. There will be constraints on this and you need to account for these. So that seemingly puts this all into question. This is why we really need to account for this if we want to make any claim of this being something that you realistically can do. Which is why what we've been spending a lot of time on now is a Python module called PAseos, which simulates the environment for operating or actually multiple spacecraft. Because we are particular, so the two things, this event today is onboard machine learning, but our research in particular is also on this decentralized aspect. So we want to have multiple spacecraft operating together. So you can see here, for example, we have two satellites that are kind of opposing orbits, which you on the right, you see sometimes they can see each other when it's green. When it's red, they can't. And we model already their charging of when their solar panels are in the sun. And of course their orbits. Now, the idea here is that we want to incorporate as much as possible of these constraints to create something that allows us to realistically make this claim that this will work in orbit or in space in general. And because we have the hardware, thankfully, thanks to UNI, but we have a few devices that are actually made for running on satellites, but we now need to also account for this. And we're building it in a way, because we don't want to build this as a one-off thing that publish a paper and we're done with it. No, we want it to be very, very application agnostic so that you can use it. So I said before, activity often, meaning that you can even use this beyond machine learning. You can specify what kind of thing you want to do, and this will help you model, okay, it takes this long, so you use that much power. You need to transmit this much data, then we model that as well. It's fully decentralized. It runs on each device individually, so it's completely independently. And there is actually no reference or use of any machine learning framework at the moment. So you can use this with whatever you want to use it with. And as you can see in the bottom left, so we are, of course, still in the process. This is not quite a simple project. We have some, already simple orbital mechanics in there. We don't want to go too crazy on that. We have a bit of the power budget modeling in there, and we're working a lot on the, you see the communication is already partially in there. We have some ideas for radiation. Need to work a lot more on the thermal aspects as well. But this is a work in progress. It's open source, and we are very curious to also chat with you about this, because actually this is not only the research that we want to do, and why we all invited you here is not to show you a half-finished product and be happy. It's actually because the kind of second part, what our goal is here, is to start building a bit of a community around this topic. Because we're really interested because we can see we have the experts here in space matters. We have a lot of people with AI, especially edge learning. And we want this to become a regular thing, to meet, to exchange, and also with less presentations and more interactions in the future. But of course, we need to first introduce a bit what we want to do. And of course, somewhere at the intersection of academia, public and private sector. And we have a lot of ideas what we can do in terms of events. We are not really settled on anything. And it's actually also what we would ask of you to get some ideas on that. And that brings me actually now to the next point, because now we will be doing a few breakout rooms where we are trying to figure out what are the things we can do with this. So what are the things that you think, what are the applications you want on board, and how can we facilitate this? And also concretely to PAseos, the Python module mentioned, what do you think? Like, do you see any use cases already, maybe? Or if not, what actually is there that what's missing for you to make this interesting? Because we want this to be broadly usable. And of course, also in the organization of this event and this community building, we really super curious to hear what you think brings the best value to all of us in terms of the types of events you would like to see, the formats, to figure this out. So now I would ask you, so for the online people, the question there, we will be organizing breakout rooms to split you up. Please share your thoughts. Ideally, it would be the best, because we know we have a lot of people and we cannot have dozens of moderators keeping track. So if you could write the main, well, like one sentence on what do you think, like it doesn't have to be all the questions, what the main points that you felt in your breakout room that came from this and what you would like to see in the chat, then we will be reading it and we will make decisions based on that. So that would be great. We'll also shuffle, by the way, after 12 minutes, so don't be alarmed. We'll randomly throw you in rooms in a second, and in 12 minutes later, you will be thrown into rooms yet again to make it a bit exciting. And for, of course, you're here on site. We're not going to throw you randomly into rooms, but feel free to grab a coffee and a drink, and let's have this conversation in person. And we'll meet here again, I think, in about 25 minutes then to have a few final notes and to see, especially to also say goodbye to everybody online. And now, happy talking, happy mingling, and talk to you in a second. Perfect. Let's see. Let's gather around just for a second. Because before we completely drop all agenda points, we wanted to briefly thank you all for joining us, both online and in person. And we would love to hear more of your thoughts, where to go. And thanks so much on site. Please stay around as long as you want. We'll be here as well. Online, I think we'll have to close now to give to wrap things up there. Thank you so much all for joining. Thank you to all our speakers. And I think Minute maybe, or Gabriele, you want to add?
Just want to thank you again, everyone. Feel free to reach us for any question, comments, especially from the online audience for which we could not talk directly now. And that's basically it. I think Pablo, you said basically everything. So thank you very much.
Big shout out to the AI Sweden team for fully supporting, to the team in Gothenburg, for the people in Edge Lab. Thanks a lot. We are available for questions and we'll send out the presentations.
Yes,
I think
I forgot to thank you a lot to the production team.
Thank you a lot.
Well, it was a tremendous help, and we couldn't have done it. And let's hope to do more chats and the likes in the future.
Absolutely.
Thank you.
Thank you. Bye.